Hello, Kaiva.
Yes, hello.
Are you there?
Can you hear me? Um, Hello. Can you hear me now?
Yeah, Kaiva, you're audible.
Okay, great.
Yeah.
Yeah. Good morning, folks. Welcome to this short session. Um, I'm happy to be here and share a quick preview of the course we intend to take online. Um, Before diving into the subject matter itself, I thought I will briefly introduce myself. I have been in the industry for a fairly long while, right from 91, 92. And I have worked on various aspects of system programming. Um, Much of the last 15, 16 years has been purely on the Linux OS. And I'm happy to have contributed to both open source as well as closed source projects. I have a few small contributions within the Linux mainline kernel, and as well as on other projects. I maintain my own GitHub site as well, where there are some small interesting pieces of code. Um, Besides that, as kindly mentioned, if you can see the screen, this is the book that I authored last year, and it's available on Amazon as well as on the Pact website. Um, these experiences are helping me learn more and more because, as we all understand, the subject matter is truly vast. In fact, this year I'm working on my second book, and you can see a preview of it over here on Amazon. This book is on, in fact, on kernel development, and hoping to have it released in August or September. So, that's the thing. Coming back to what we intend in doing, what I thought I'll show you all. Okay, sorry, give me a moment. Yeah, what I thought I'll show you all is the kind of matter that we intend to provide. So this is the Linux kernel internals course, and I will just scroll down. Basically, this is the content matter that we'll be looking to provide as a full-fledged online session. Um, it it actually spans a pretty vast amount of ground and in a fairly short time, so that by the time you are done with this, you really do have a solid grasp on the fundamentals, the essentials, the architecture, etc. And of course, very importantly, in my opinion, the ability to write code hands-on. Um, we will be going through fundamentals. In fact, in today's session, I intend to take up a little bit of this, perhaps around this much, and just give you an idea about these things. In the actual course, we will be covering the kernel source tree. We'll be downloading it. We'll be working on it. We will cover the build procedure. And very important, we will dive early in the course. We will dive into writing kernel code. So, one can write kernel code by actually delving into the kernel source tree, modifying it, rebuilding it, rebooting the machine with the new kernel image, and testing your changes. That's called doing it inline. But that's a difficult way to do it. There is a much nicer way to do it. There's a framework called the Loadable Kernel Module, or the LKM. And with this framework, you can generate an object file which you can insert into a live kernel at runtime. And it becomes part of the kernel, and you can test your changes. So it's modular in that sense. An introduction to writing a hello world kernel module is again something that I'd like to show you today. So, with these two things, a little bit about the Linux kernel architecture over here, and a little bit about writing a kernel module is the intention for today's short session. So, folks, there is, of course, this is in a sense the tip of the iceberg. There is a lot more to learn, study, and understand in detail, which we will cover in the actual course. As value addition, there are various ways to debug the Linux kernel. And, I think as we all understand, software does not come out in a perfect state. In fact, far from it, unfortunately. And very often we have to go back, identify and fix bugs. And that process is, of course, called debugging. There are many, many tools. In this particular course, I will give you a feel for perhaps a couple of them. We will have a separate dedicated course on kernel debugging, by the way. But in this particular course, we have an intro to kernel state analysis with Crash. Crash is one of the really powerful debug tools. You can think of it as a superset of GDB. So anyway, besides that, we go into pretty deep details of the Linux kernel architecture and a root data structure called the process descriptor. Memory management is an enormous topic, but it's a very, very critical topic. And this topic is given several hours of time, because understanding this topic helps you to truly understand how the OS works at a close to bare metal level. Very often many of us have conceptions and misconceptions about what exactly is virtual memory. We intend to clear up all these things in a proper fashion in this place. We intend to go deeper than that. We intend to look at hardware paging, and we will use the Intel machine and the ARM machine as examples. We intend to go into ARC-independent stuff and explain how Linux uses virtual memory in quite a lot of depth. If any of you will subsequently work on writing kernel code, very typically writing a device driver, which again will be one of our offerings. Allocating and deallocating memory within the kernel, of course, we're not talking about the user space analog, is an extremely performance critical thing to do. And if you're not aware, you might end up using APIs that are suboptimal for the job at hand. So the deal is, once you understand things at an internal level, you will appreciate that there are many ways to do things, and which is the best way in which situation is a very critical skill to have. So we will delve into all of that. Understanding the kernel memory map on Linux. And I will be showing this for ARM as well as the x86. And various miscellaneous stuff. There's something called the out of memory killer. How do we handle page faults? How does the kernel view the process, etc. The next major module is the kernel CPU scheduler. And as we all appreciate, it's another core part of the OS. How does the operating system actually schedule processes and threads to run? What is the kind of algorithm it uses? In fact, interestingly, over here, we learn that there isn't just one algorithm. There are several, more like 5 or 6 of them. And which is the default? What does it mean? It's called the completely fair scheduler. What does that mean? How can we use Linux as a real-time system? Over here, we mean soft real-time. But very interestingly, you can also convert Linux into an RTOS, a hard real-time OS, by applying a patch, an external patch. So these things will be explained. The motivation and the need for control groups, a very much used feature in today's embedded as well as server systems. This is for resource control and allocation. And again, a debug tool called ftrace, the kernel's way of tracing absolutely everything that's happening under the hood. These things help us understand in great depth what is really going on within the operating system. It helps us debug as well. Finally, this topic isn't complete without this really critical thing. Concurrency is an issue. Threads, processes, they run in parallel with each other. Unfortunately, we can end up with data races where, using a global at the same time will result in corruption. So where do these situations occur? Why do they occur? On multi-core is one of the situations, but it's not just that. Even on uniprocessor, hardware interrupts cause concurrency. Scheduling can cause concurrency. Several other things. We discuss all this in quite some depth. We talk about locking as a way to solve concurrency issues. Interestingly, it's one of the ways. There are other ways. Locking is very common, and unfortunately, locking can result in deadlock if not done very carefully. So, what is deadlock and how can we prevent it? This is again a very critical thing to really understand. The actual locks, the spin locks, the mutexes, the semaphore, the specialized locking operatives like atomic locks, reader-writer locks, barriers, etc. All this will be discussed along with an introduction to what's called RCU, a lockless technique. So anyway, folks, this is just to give you a flavor of the detailed course. Like I said earlier, that's not the intention here and now today. So for today's session, I suggest we jump into OS architecture, if everyone is okay with that. So I will move on to that. I'm just checking over here. Everyone is fine with what's going on so far. Then I will proceed. Is it clear to everybody? So great, I take it that it's all okay, and we can move along. Thank you. So folks, you can use the chat window if you want to ask me something. Perhaps during the flow of my talk, I won't be able to stop and answer you right there and then. I will take it up later. You can alert me. Okay, great, guys. Let me okay, so Abhijit has asked, does this course explain about everything? Well, I am not very clear what you mean by everything. If you are referring to what I've shown you over here, then the short answer is yes. We intend to cover all these topics in the actual online course. Is that all right? So Abhijit, again, I repeat, today we aren't explaining every module. It's only an introduction. But when you sign up for the actual kernel internals course online, at that point in time, yes, we will be covering all these areas. Is that okay? Folks, we take that up separately. That will be announced on the website, things like the fee and stuff.
Kaivan, if I may just intervene for a minute. Is it
Yes.
okay? Yeah. Hi, folks, including Abhijit and every other participant. Details regarding the course fee, the course schedule, and when it will be happening, the timings, all of these will be addressed post the completion of today's session, because I think the session would needs to have a little bit of continuity. Once it's done, we'll maybe take that up and we will have a communication. We'll also be sharing a mailer communication with you. So all these details will be conveyed. All right. So we can proceed, I guess.
Okay, so good, guys. Let's move along. So what I'm doing is I'm just displaying to you the PDF that I use for an introduction to the architecture topic. Even, before I show you any slides from here, maybe it's a good idea. Okay, hang on a sec. Let me just look for the whiteboard feature. Yes. Yeah. So, folks, I hope you can see this over here. And okay, so here's the thing. Okay, let's ignore that. Let me go back here. Okay, let's do this. Let's draw this box over here. And let's say this is the CPU. We all know that the CPU is where machine instructions get executed, and therefore the whole computer works. Of course, a CPU is not enough. We need peripherals, we need RAM, we need storage, etc., etc. But for our discussion purpose now, let's just look at this. Now, what I'm actually trying to get at is, the computer, the general purpose programmable computer, was invented a very long time back. A working model was available in 1945, as early as that. What did it do? It executed machine instructions, just as it does today. However, the machine instructions had to be fed in over teletype, over punch cards, and very archaic systems. It was very difficult. Today, what do? We write high-level code. We use a programming language such as C, C++, or whatever, Lisp, doesn't matter what, Java. Along the way, a compiler translates our high-level language code, which is kind of English-like, into what we call assembly language. It's known as the second generation. And assembly language is translated into individual machine instructions, opcodes and operands. And this is really what flows to the CPU and makes the whole thing work. Ultimately, it's machine instructions, right? Now, having said that, yeah, having said that, one thing was noticed by system engineers. It all worked, and it worked pretty well, but security was lacking. So what do I mean? So let me give you an example to illustrate what I mean. If you do a little web browsing, if you go to Intel's website, and if you look up their ISA, Instruction Set Architecture document, you will find a big fat PDF, and you will find many machine instructions which you can program directly using assembly language if you're willing to do so. Now, one of those machine instructions is explicitly used to halt the machine. So guess what it's called? Well, it's called halt. So guys, think about it. If we write an assembly program and we issue the halt instruction, the CPU will halt. Now, imagine that a malicious programmer inserts this into the instruction stream. He will be able to halt the whole system, in effect. Now, that's not really desirable, right? So what system engineers decided is, let's change the way this works. Let's provide certain instructions which okay, hang on, which can be issued by everyone, by all programs. Okay, and let's keep certain machine instructions, like halt being a really good example, which can be only issued by a privileged program. So folks, you can perhaps guess what I'm getting at. The reality today is that we have a dividing line, and it looks something like this. Everything over here is called user space, everything above the line. Okay, yeah, that's better. Everything above the line is called user space. And as you can probably guess, everything below it is called kernel space. So what has happened actually is that we've got a minimum of 2 levels of privilege. This is called execution privilege. Every line of machine code, every machine instruction that executes on the CPU is executing either at user space privilege or at kernel privilege. That's what I'm trying to make clear over here. So folks, here's the deal, and it's kind of easy to understand. User space processes can only issue certain machine instructions, which is a subset of all available machine instructions for the CPU. The kernel, on the other hand, is free to issue any machine instruction at all, including the halt. So you see, we have privilege now. Um, to really make this discussion more clear, I'll tell you the actual case. Every microprocessor has been designed to have different privilege levels. The Intel engineers, when designing the 8086 essentially and onward, they came up with this idea of having 4 privilege levels. Now, those privilege levels go from 3 to 0, 3 to 1, 0. So what does it mean is the obvious question. Privilege level 3 is the least privilege. And folks, have you guessed it? That's this one over here. Intel calls it the ring level. User space is ring level 3. And kernel space is at ring level 0, the most privileged level. In other words, on an Intel machine, the operating system runs at ring level 0, completely privileged. And user space, I haven't explained it. What does user space mean? It's simple. The processes that we run. In other words, the applications. All the applications are running in user space. We know, right? A process is an instance of a program in execution. For example, you run VI, it's running here in user space. It's running at ring level 3 on an Intel machine. It's non-privileged. It can only issue a certain subset of the instructions allowable on the processor. But the kernel, the operating system, runs at ring level 0. It can basically do anything. So guys, this is a really important thing to understand. But I know you have a question. If 3 is user space and 0 is kernel, then what is 1 and 2? Okay, these are middle level privilege levels. Intel does not insist that the operating system designer uses them. As a matter of fact, they are unused in today's modern operating systems. Linux, Unix, and Windows, and of course Mac. Mac is nothing but a specialized Unix. They all use ring level 0 and 3 only when running on Intel. You see, that is the reality. However, in the early 90s, when when VMware was inventing virtualization for the x86, which was a really difficult job, and they've done an amazing job, they used ring level 1 for a while for the hypervisor code. Interesting, huh? They actually did that. Today, let's take Linux as the realistic OS of choice. Today, Linux's hypervisor is a kernel component called KVM, kernel virtual machine. In fact, the largest cloud provider on earth, Amazon, AWS, they use it. KVM runs at kernel privilege. It's the hypervisor. It runs over here. And very interestingly, remember what I said, we will also, oh, sorry, give me a second. I said that we will look at kernel modules, right? Well, KVM runs as a kernel module in most setups. Interesting, right? In fact, guys, something interesting to make this discussion more meaningful. Okay, hang on a second. I need to move this out of the way. Sorry, I will just resize these windows to make it easier. This is Oracle VirtualBox. And it's just a custom Linux that I've got running. Sorry, give me a moment. Okay, there we are. This is Linux, guys. We have a terminal window, and guess what? ls mod is list modules.
Sir, we're not able to see that, sir, whatever you shared the screen.
Oh, I see. You're not able to see the
Yes.
virtualization window.
Yeah.
Oh.
I think you have shared only this notepad. If you share your full desktop, it will be visible.
Right. Actually, I tried to do that initially.
You can do one thing, sir. Stop sharing your screen, and again you can share your whole desktop.
Sure. Let me do that, folks. I'll stop the share and do it again. Just give me a moment, please.
Yeah. Now we are able to see your desktop.
Can you see the Oracle VirtualBox VM?
Yes, we are able to.
Okay, excellent. So you can see that I've typed lsmod pipe to grep kvm. Yes. And okay, interesting. It's not running over here. Folks, sorry about that. I will move back to my native Linux system. And give me a moment. And maybe I will just try that once again. So over here, it very much shows up. Guys, let me do this one more time using regular expressions. And this time, it's, I think, very clear and obvious. We have the KVM kernel modules running. This is actually the hypervisor, guys. This is how Linux does virtualization. There are a couple of kernel modules. Okay. So anyway, I'm going on.
What is, pardon, sorry. Why the hypervisor came into picture? You executed a simple ls command, right?
No. Please see clearly. It's ls
module. Yes, ls modules.
It's a list modules. So KVM is a kernel module. You understand? It's in kernel memory. It's currently running in kernel memory. That's why it's showing up over here. You know, see, this is, I just did this. Maybe it's a little early for me to do this. I did this to show you guys that it used to be running at ring level 1, which is what I was explaining earlier. You recall?
Oh yeah, got it.
Yeah, so that's how this whole thing came about, which reminded me about nowadays it doesn't run at ring level 1. It runs at ring level 0, kernel privilege. It runs as a kernel module. Okay, that was the only point I was making. So folks, I'll just bring back the whiteboard over here. Yeah. So now that we've got this again, in fact, why don't I do one thing? I'll close it for the time being, and I will scroll ahead of some things over here because I want to show you guys this. So do you see this diagram, folks? And in
Your
this,
screen is completely off now.
you can't see anything on the screen?
Yeah.
I see, I see. Give me a second. Let me try and resolve it.
Yeah, it's open now.
Yeah, it's fine. Okay. Yeah, folks, if something goes wrong, please inform me so that I can try and correct it. So now we can see this, right? So guys, this is how Intel usually represents it diagrammatically. You can see we have 4 ring levels: ring 0, 1, 2, and 3. So I've colored ring 3 in green, that's user space. Ring 0 in red, that's kernel space. Okay. R1 and R2 are currently unused on all modern operating systems: Linux, Unix, Windows, Mac. Okay, this is how it works on Intel. Now, in a sense, we've gone a bit ahead. Let me come back to something we were talking about earlier. So you remember that I showed you this whiteboard, right? Now, on this whiteboard, this is user space, this is kernel space, right? Application processes run in user space, and obviously the kernel runs in kernel space. But this is a simplified diagram. A better way to show it. Okay, one moment, guys. Okay, a better way to show it is perhaps like this. So folks, this is a diagram from the internet. User applications is nothing but processes. For example, VI, Chrome, Firefox, etc.
We lost your screen again.
Oh no. Okay. I'll redo it. Something peculiar.
Sir, you can share your overall desktop, sir.
That's
Yeah.
what I've been trying to do. I've been clicking on desktop. That's what I've been doing. But something seems a bit iffy. In any case, now is it okay?
Yeah, it is okay now.
Okay, okay. So folks, this is user space, this is kernel space. We've got applications here, we've got the C library here. You can see that this is where the kernel runs. Now, if I scroll down a bit, this is a much nicer diagram of the same thing. This diagram is taken from over here. I've mentioned it. These apps are nothing but processes. And I think, as we all understand, processes can consist of either one thread or multiple threads. These are the processes. The C library is always in play. Let me explain why that is the case. I will come to it. Just let's hold that for the moment. This is kernel space. So you see, Linux is a modern kernel. It's a sophisticated and, in fact, a pretty complex piece of software. It's not just one program, of course not. There are many, many modules, and that's what is being shown over here. You can think of these as subsystems. We've got process management, memory management, FS, etc., networking. And at the low level, we've got all this stuff. So now I come to another, really critical point. Okay, guys, I think the reason it's been going is when I switch to that whiteboard. I think I will have to again switch back to the desktop. So now I think you all are seeing the whiteboard, right? So folks, over here, what I want to try and explain and make clear now is, you remember I said that we've got processes here, and this is the kernel. Now, we do understand that the kernel provides services to user space. For example, if you want to write a chat program, then you need networking, isn't it? Now, I type a message and I want it transmitted across the network to some other process on another machine. Now, am I expected to write the code for that? Of course not. That would be far too complex an undertaking. TCP/IP is already a reality. We don't need to reinvent the wheel. So guys, you know what I'm getting at? The Linux kernel has all this code inside of it. It's got the implementation of UDP/IP, TCP/IP, etc., etc. All we need to do is use it. So that brings up the fundamental question. We understand that, you know, the networking code is here inside the Linux kernel. However, how do I get my application to reach that code? How do I talk to it? So you see, the problem that we are facing is that this code is running at ring level 0, kernel privilege, whereas our process is running at user space. So how do we make the transition? It can't be automatic. There has to be something special that happens to make the transition from user mode to kernel mode. And that is done by issuing a special API. That API is called a system call. So guys, this is a very key point here. Okay, sorry. I'm just trying to grab hold of this window. Yeah. Yes. So folks, coming back here, we understand that applications can issue APIs, which is nothing but function calls. Among those APIs, we can broadly say that there are two types. Let me quickly switch back. Sorry. Okay. One type of API is via the libraries. For example, the C library. These are user space APIs. And the other API are the kernel APIs. Now, we can't access the kernel APIs directly. So the C library, glibc, provides us with a special interface. These are called system calls. When you issue a system call, control crosses from user mode into kernel mode, and kernel code starts executing. For example, I'm sure you know that if we want to do networking, we need to use socket system calls. There are APIs that are available to use sockets, you know, right? Haven't we seen things like this? You can use this API to set up a network connection, the socket. What really happens is that your process makes a transition from user mode to kernel mode and starts running this code, which is deep inside the kernel. That is the power of a system call. So guys, that's what really happens. We actually, the word used is trap. We trap into kernel space. It's literally like a processor interrupt or exception. Sorry, excuse me. So the system call switches us from user mode to kernel mode. Having told you that, see guys, these are the same diagrams in more detail. Do you see system calls here? They live within glibc, all the system calls. So when an application issues a syscall, it can come into the kernel, into any of these layers. depending on the system call emitted by the process. And the process will further work within the kernel, perhaps using device drivers to do more stuff. So to take our example of network, obviously we will go into the network protocol stack, we will execute TCP code, internet protocol code, and from there we will go to layer 2, MAC or device driver. In fact, it will be the NIC driver, the network interface driver. And that code will talk to the hardware chip, and that will transmit or receive packets for you. It's a very complex activity, and it all happens simply by Userspace issuing a few system calls. That is the power of layering, and this is a layered architecture. So guys, that in a way, that is the whole point here. We can sit comfortably over here and we can write very sophisticated applications which uses stuff deep down over here. And we don't have to understand all those details unless you are studying the kernel, which is of course our whole point. We would like to start understanding how at least some of these things work. You know, the Linux kernel is a big fat beast, guys, as you can see over here. In our actual online course, we will be covering parts of these, not the entire thing. It's simply too vast to cover the whole thing in one course. So anyway, folks, this has given you all some idea about the architecture. In fact, to finish this example, let me come to one more typical and interesting thing. So guys, let me just make some space over here. Okay. Yeah. Now let's do this. You've written hello world and you've got a.out. Now a.out, how does it work, guys? I think you know, right? It's the printf, isn't it? Here you write hello world. Now hang on a sec, how does printf work? Maybe we were taught that printf writes to the monitor. That's not very accurate. Printf actually writes to standard out, but it's a little more complicated than that. Printf is a library API. This goes to glibc. You understand that, right? So, guys, this is glibc here. It spans the whole thing, okay? Control will come from your printf in here into the printf code. And glibc's printf code only has the intelligence to perform string formatting. That's it. For example, using the \n, %s, %d, %.3f, etc. After that, how does it come to the monitor? Okay, so guys, here's the really interesting thing. Give me a second. Yeah. Printf issues a system call called write. And the write system call is what gets us into the kernel. Do you follow? And this is where the kernel code of write resides. And this is where the magic happens. Well, it's more complicated than that as usual, okay? The reality is there are many more code paths to follow, and we finally end up inside a component called the device driver. And this is the piece of kernel code that actually talks to the hardware chip. And that's how it comes ultimately onto the monitor. So you see, even these small things that we take for granted are really complex under the hood. There's a lot of work that's been happening. So guys, this is what I wanted to explain about kernel architecture. One more critical point remains that I want to, finish this off with. And that point is this. Very broadly speaking, there are two kinds of operating system architectures. One model is called the monolithic kernel, and the other is called the microkernel. In the monolithic kernel, and again, I won't explain this in full detail, because to be honest, we need to cover some memory internals to really appreciate it fully. So for now, I'll just give you the basic version of it. In the monolithic kernel, we consider this entire architecture to be one piece. Monolithic means single piece of stone. That's the meaning of the word monolithic. A monolith is a single piece of stone. So this whole thing is considered one piece. Don't stress about that right now. I'll cover these details when we do memory management in the actual online course. The key point to understand now is this. Many of us have this misconception that the a dot out process, when it calls printf, now printf calls write and write calls the kernel. That's wrong, guys. There is no kernel. There is no process called the kernel. The kernel is just code and data residing in RAM, which is only accessible at ring level 0. That's it. It's not a process. Okay, that is a key point. So to go further, when printf calls write and write causes the mode switch to happen from user mode to kernel mode, the process a dot out is now running the kernel code of write at kernel privilege. This is called monolithic design. It's one piece. It's not like the kernel is running the code. The process is running kernel code. And guys, that's how it really works. And this applies to absolutely everything, because all our applications are ultimately issuing system calls. In fact, including the JVM. How do you think the Java virtual machine works? By issuing syscalls. And that process is running the kernel code at kernel privilege. And that's how the whole system works. This is called monolithic design. Folks, let me switch back to the desktop. Sorry, give me a second. Yeah, so over here, guys, this slide, the instructions in black color are user mode permissible. The instructions in red color are only kernel mode permissible, and they include the halt. You remember? Okay. I'll not get into everything over here. Stonehenge, these are monoliths. Okay. So folks, that's what we are coming to. All these operating systems are monolithic. And of course, that includes Linux. In fact, it's interesting. These are most of them. All the Unixes, pretty much 90% of the Unixes and all these others shown over here, they're all monolithic. Okay. However, we have something else called microkernel. Now, the interesting thing is there are very few real world examples of microkernels. Well, what I mean is commercially viable. The main ones are QNX and VxWorks. And you will know that these are real-time operating systems. And they're very expensive. In fact, Linux has been putting a severe dent in them. Anyway, what about Windows? How come Windows hasn't been mentioned? It's an important OS. So guys, Windows claims to be a hybrid. It claims to be both monolithic and microkernel. And Wikipedia shows us this diagram where you can literally see this is monolithic. All the kernel stuff lives in kernel mode. This is microkernel. It's a tiny kernel, a microkernel. Most services still execute in user mode. They're called servers. And in hybrid, it's a mix of both, which Windows apparently uses. So guys, we need not go into more detail about this. It's just a conceptual understanding is necessary. The key point, Linux is always this. It's monolithic. Okay. So folks, that covers what I wanted to say for today's session on kernel architecture, Linux kernel architecture. I hope it's been enlightening. What we'll do for a few minutes now, it's actually more of a demo rather than trying to teach this topic in depth, to do with the kernel module framework. Because folks, to be honest, a few minutes is not sufficient to explain that properly so that you understand everything. Instead, what I'll do is I'll just demonstrate to you the basics, because it's simply something very interesting to see. So guys, give me a moment. I will just load up my system. Just I will stop the sharing. I'll come back to you in a moment. I'll just move across to some code where I can demonstrate the kernel module. So hang on a moment, please. Um, yeah, sorry for the delay. So guys, are you able to see my screen now? Hope it's okay. You can see over here I have a couple of source code files, and I'm running in my VM, just to, it's always easier and nicer to run kernel code in a VM, because kernel code can actually crash your system. So by running in a VM, we protect against that, because in the worst case, you just shut down the VM. Your desktop, your laptop is insulated from those changes. So over here, guys, is a quick demonstration of how we can write kernel code using the LKM framework, the loadable kernel module. I take it that this is all okay. You all can see what I'm showing, right? So let's proceed with this. Let me open this using an editor. I'm just used to using GVim, which is VI in a little more graphical format. Folks, it's really short and sweet, but here's the key thing to remember always. We are now talking about kernel code. This is not user space. So, the first two lines of code are the hash include, of course. These are not under user include. These are kernel headers, and therefore you need them on your system. These will be available when you install a package called kernel headers or Linux headers. So I won't go into all that detail now, otherwise we'll run short of time. I'm just informing you that there are certain prerequisites. You need a compiler, obviously, and you need the kernel headers package installed, then you are able to hash include these include files. Module license is obviously a macro. You must specify under what license you are releasing this piece of kernel code. Now, guys, this is another of those controversial topics. I won't get into details here and now again. The point is this: if you are intending to contribute your code upstream to the kernel community, to the mainline Linux kernel, there is no choice but to use GPL, the GNU General Public License. You have to, you must. But if it's for your own project, your own product, then it's even possible to release it under another license or under two licenses, dual licensing. So over here, I'm using MIT, which is a nice and simple open source license. And I'm also saying that it is available as GPL. Anyway, we won't really go further into that. The next thing to understand, at the bottom of the kernel module, we have two macros. The first is module init, the second is module exit. Okay, here's what you need to understand. I will need to switch back to the whiteboard. So great, we're here with the whiteboard. So guys, let's use another color, let's say blue color, and let's say that you want your kernel module to come here, right? So this is your loadable kernel module, your hello world. But of course, how do we get it in here? So to get it in here, you have to issue a Userspace application. You have to run this app, and you can guess, right? Insert module. The insmod command, the path name is the parameter. It gets your kernel module into the kernel. Conversely, when you are done with it and you no longer want it, you remove your kernel module with the rmmod command. I will demonstrate these things, guys. Okay. So the key point for now, insmod gets it in here. Okay. It's now in kernel space. Having said that, what about programmatically? How will it work? So what I'm trying to get at is, see, this is a kernel module. There is no function called main. This is not an application, nor is it a library. It's a different beast altogether. It's kernel code. So how do we get control in the kernel? Okay, so folks, I will just switch back to the desktop view. Give me a moment. Yeah, so I hope you are able to see this again. So here's the key point. There is a macro called module init. The parameter to module init is the name of a function. In other words, a function pointer. With the C programming language, you can just give the function name. When you use module init, the kernel LKM framework understands that when insmod is done successfully, call this function. And that's how we get control. So the moment a successful insmod of this kernel module is done, the function hello init will be invoked. You can think of it as being analogous to a constructor. Now, of course, this is not object-oriented programming, but nevertheless, it's an analogy that we can use. In a similar fashion, the module exit macro is to specify what to do when rmmod is called. So guys, now it's clear, right? When rmmod is called, the function hello exit will be invoked of your kernel module. So now that we understand that, we can actually look at the code of hello init and hello exit. Now guys, our whole objective here is to simply say hello world, nothing more. Now, any C programmer knows that the way to emit something is via the printf. But guys, we can't use the printf. Why not? Simple. There are no libraries in kernel space. Absolutely none. There is no concept of libraries as it exists in user space. However, we need some common routines, right? We need something equivalent. So it has been done, guys. Allow me to show you all something interesting. On my laptop, I, of course, have the kernel code installed, guys. This is an example of the Linux kernel. Okay, this is the actual source code. So I just want to, show you all something. Under the folder called kernel, there is so much stuff. There's so much code. And do you notice a subfolder called printk, which I've highlighted over here? The printk is the kernel equivalent of the user space printf. And here's the C code that actually implements the printk. Linus Torvalds wrote it first. So folks, we can use this API here. We can actually emit a printk, which is very similar to the printf. And the output will go to the console. So in its simplest form, guys, do you notice? Hello init is over here, hello init. We mark the function static. That's good programming practice. It's private to this module. The return is of type integer. That is important. It takes no parameters. The function that we emit is just this, pretty much just this low line of code, the printk. It's not printf. Now, just glance at the printk. It's almost identical to the printf. We do hello world \n, but there seems to be something here. This is a logging level. That's all it is. It's the level at which this message is logged. So guys, let's come back over here and let's do something interesting. I will switch to my kernel folder and I have cscope installed. Cscope and ctags, very important to use them as code browsers. And here's, okay, actually to keep this simple now, I'll just move into any code inside the Linux kernel and I'll use ctags to say kern_alert. And check this out. We're in a header, include linux kernlevels.h. Okay. And within that header, these are the 8 possible logging levels that the printk can be emitted at. You know what, guys? It's just a string. And the string is a number from 0 to 7. That's all it is. So, don't get very confused by this. I'll briefly explain the purpose. For the time being, we just see that we are emitting the printk at a pretty high level, kern alert. This is the lowest possible level, kern debug. And this is the highest possible, emergency. The comment tells you what it means. It's very clear with the comment. Okay, so the developer, the kernel developer is expected to emit the printk at the appropriate logging level. Over here, as a demo really, we use kern alert. Kern debug or kern info would have been fine. And we say hello world. That's it. The next thing we do, ignore this code, I'll come back to it. The next thing we do is we return 0. Notice it's data type integer. Returning 0 has a meaning. It means you're telling the kernel framework that you are successful. This is very critical, guys, because if you don't do this, the kernel might assume that you have failed. And in older Linux kernels, it would actually unload the kernel, the kernel module from the kernel space. So here is a demo of that. If you make this if 1, then this code will become runnable. And I return -e no mem, which essentially means I'm saying I'm out of memory. So guys, this leads me to another really key point. Inside the Linux kernel, right, we have a return convention. It's called 0/-e. You return 0 on success and you return negative errno. You've heard of errno? Erno is the user space global, which is in fact in your uninitialized data segment. This will get initialized to -e multiplied by -1. In other words, the absolute value. So if we return -e no-mem, Erno will become e no-mem, which tells glibc that you failed because you are out of memory. And this is the error message that will be seen, which is, appropriate. So guys, don't let all this confuse you. If you intend to return success, return 0. If you intend to return failure, return the negative Erno. That's what it boils down to. I hope that point is okay. It's an important point. But we're not done yet. Assuming we've done the insmod, you should be able to see the hello world, and then it will return 0 for success. After that, what happens? Nothing. It just remains in kernel memory, your kernel module, doing absolutely nothing. When the user does the RM mod, this function will get called, hello exit. Notice there's no return type, there's no parameter. And over here, we basically say goodbye. That's it. In real kernel code, like a driver, this is where we would perform cleanup. And conversely, in the init code, this is where we perform initialization, perhaps allocating memory buffers, initializing registers, and over here we will do the complement, the opposite. So guys, this is a very basic loadable kernel module. This is a hello world. Now, all this is meaningless unless we can actually try it out and prove that it works. Now, to prove that it works, I will have to build it, right? And for that purpose, I have a make file. Now, guys, because of time constraints, I will not be able to explain the complete make file. This is how the make file looks. In fact, over here, it's a little more complex because I also take into account cross compilation, for example, for the ARM. But these are your basic rules: the build rule, the install rule, and the clean rule. The build rule is the default rule. Okay. For now, let's not worry about these details too much. This is, in a sense, the most important line. We are telling the kernel that we are building a module. The module should be hello.o. So the kernel understands that it will look for the source file called hello.c. It will build hello.o, and further, it will link other sections on to create a hello.ko, kernel object. That's the kernel module. So folks, why don't we just try it out? I just type make, and if all goes well, it will build. So it looks like it has gone well. This is a message that I have inserted in the make file. We can see we are building for the x86 because, of course, this is an x86 based virtual machine. Cross-compile environment variable is null. The kernel we are building against is this Ubuntu kernel, 4.15.0, whatever. Anyway, now have a look. Several files are generated. You can ignore most of them. The key file is this one. That's the kernel module, the hello.ko. So guys, this is our ultimate end result. I'll show you an interesting thing. You can use a utility called modinfo to examine the kernel module. So it tells you that this is the path name. Okay. This is the license. This is like a checksum. You can think of it as that. It's called source version. This is the name. And this is the kernel it's been built against. So guys, this brings us to a very critical point. This particular kernel module will only work on this machine or a machine which matches this, meaning only this particular Ubuntu kernel. It won't work on any other, unlike an application which you can compile and run on several Linux machines. So, it's not really binary compatible. Okay, you would have to rebuild it on every target. Anyhow, let's not worry about all that too much right now, folks. Again, this is the kernel module. So see, here's a quick proof of concept. If I grep for hello, it's not there. But now let me insert it by using the insmod. Guys, what you will find is it's going to fail when I do this. Why? Let's check it out. You see it failed. And the reason it failed, security, operation not permitted. Folks, think about it a moment. A kernel module runs at kernel privilege. If I want to write a virus, this is the way to go. Because you're running, in a sense, even better than root. You are running at the operating system privilege level. You can do absolutely anything and everything. Well, almost. You see my point. So folks, in a nutshell, not anyone can do insmod rmmod. You need root access. That is the security. So guys, we know, right? We use the sudo application. It will ask you for your password. I key in my password, and if I got it right, it will run insmod with root privilege, and now it has worked. How do I know it's worked? There's no error message. That means it has worked. Let's do the ls mod again, and there we go. It's in the kernel. It's taking up 16,384 bytes, 16 kilobytes. This is called usage count. It'll be either 0 or positive. So guys, how come my hello world didn't come on the screen? Well, it won't. Your hello world goes into the kernel log buffer, which is in kernel RAM. And to look it up, there are many ways. Perhaps the simplest way is to use dmessage. It's a utility. I just want to look at the last few lines, so I'll pipe it to tail. So folks, ignore these lines, but look at these lines. Here is our hello world. This is a warning telling you that you're loading a third-party kernel module, and that could be dangerous. This is, more of a legality, folks. Nothing really very technical about it. The key point is that it's in the kernel. The print k has worked. So do you see that, guys? We've actually got some kernel code running. Now, what is it doing? Nothing. It's just sitting there in RAM doing absolutely nothing. So now let's get it out. So if I type rmmod hello, I don't need to give the path name. Will it work, guys? Well, please think. It won't work, folks. Because why? Security. You need to sudo it. And now it has worked. Let's reconfirm. It's no longer in the kernel. Let's look at dmessage again. And this time, we can see the goodbye message. So you see, folks, it has worked as designed. Now, of course, this is such a small trivial thing, but the whole idea was the proof of concept that we can actually do stuff like this. Now, to finish today's session, I think we are close to being out of time. You can't see it here, but I have a Raspberry Pi with me. Well, we can always do this. The Raspberry Pi is an amazing device, right? You've seen it, right? And it's cheap. It's an SBC, a single board computer. It's brilliant. It's an ARM machine, guys. The SoC, the system on chip used for the Raspberry Pi 3 is the Broadcom 2735, something like that. I forgot the exact number. Okay, here you can see it, in fact, 2837. Okay, for the 3B plus. Anyway, all that is okay. As a final point of this demo, Let me just switch to an appropriate folder where I have a shell script to SSH into my Raspberry Pi from my native Linux machine. Okay, guys, this kind of stuff is no problem. Yeah. So, folks, I'm basically performing an SSH, in effect a remote login, and I'm logged in. So, guys, interesting, right? I'm running on the Raspberry Pi kernel version 4.14, which is pretty recent. Okay. In fact, this is a distribution called Raspbian. You can always do lsb release -a, and you will see these details on a Linux box. So this is Raspbian, guys. It's a Debian for the Raspberry Pi. That's why it's called Raspbian. Okay. Okay. Without further ado, allow me to just go to the place where I have this code over here. So, folks, I have installed a development environment on my Raspberry Pi. Here is the kernel module. In fact, it's identical to the code I showed you earlier. You see that, folks? Okay, so will it work? Now we're on an ARM machine. By the way, again, FYI, cat proc CPU info. I'm not bluffing you all. We are on an ARM v7, a 32-bit ARM. Okay, actually, it's more like it's using the processor as ARM v7, but it's actually a 64-bit processor on the Raspberry Pi. But nevertheless, it's an ARM machine. That much is very clear. In fact, it's got 4 cores. It's a really powerful thing, the RPi. Okay, so folks, just like we did before, we do the make, and now it's actually building on the Raspberry Pi. And it looks like it has been built. Do you see the hello.ko? Same thing again, modinfo hello.ko. And yes, this time it's built for this, and it will only run on this. It will run on an ARM v7 and on this kernel, nothing else. So let's just try it out without further ado. Sudo insmod hello.ko. And it's done. I have sudo permissions. So let's verify this. There we are. Dmessage pipe to tail. There you are, guys. On the Raspberry Pi, we've got a hello world. And just like earlier, sudo rmmod, dmessage pipe to tail, goodbye. So guys, I'll also say goodbye with that. I hope this has been interesting and useful. As I mentioned earlier, we would love to have you all register for the full course, which goes into a lot more depth. And I think, will really get you up to speed on Linux kernel internals. It's a big learning game, folks, and you can get a head start with a good training session. Please do consider joining up. Tell your friends about it. Thank you so much for your time, folks. Hope this has been useful for you all. Thank you.